Whether you often fly or not, you probably know that most aircraft wings are assembled from multiple components. This involves riveting and mechanical fastening, or adhesive bonding in the case of carbon fiber wings. As a result, the wing surface is not perfectly smooth. Moreover, differences in skin materials and paint finishes can also affect the surface roughness. These variations indeed influence the aerodynamic performance of the wing, and of course, factors like dust, corrosion, or ice buildup can cause even greater changes to the wing's performance. So, how much impact can these tiny changes in surface roughness really have? Imagine the silky feeling when your finger slides across a smooth surface, compared to the slight bumps you feel on a rough one. Air, as a fluid, behaves in a similar way. Over a smooth surface, the airflow moves smoothly and steadily. But once the surface becomes slightly rough, the flow starts to fluctuate and turn turbulent. Usually these changes affect the boundary layer, which is only a few millimeters thick. Yet even such subtle differences can have a significant influence on lift, stall behavior, controllability, drag, and overall efficiency. I couldn't find the model file for the GA30U314 airfoil, so before starting I processed the GA30315 airfoil by thinning it. Using Python, I scaled it proportionally to achieve a 15% thickness. The program works for any similar airfoil when adjusting the thickness ratio. I've uploaded it to GitHub. Feel free to check it out if you need it. To better visualize and verify the computational results, this study builds upon the surface friction coefficient CF distribution obtained in the previous video, and further introduces two additional parameters: the transition criterion, represented by the ISO surface, indicating the 50% point of laminar to turbulent transition, and the turbulent kinetic energy TKE field for comparative analysis. Let's start with the skin friction coefficient, CF. When the surface becomes rougher, the most direct effect is seen in the relationship between wall shear stress and dynamic pressure, that is, CF. A rougher surface increases wall resistance, making it appear as though the airflow sticks more tightly to the surface. We can see that under a rougher surface, the overall value of CF increases, indicating a higher wall resistance. At the same time, the point where CF equals 0, which represents the onset of flow separation, appears further forward and occurs earlier on the rough surface. Next, let's look at the transition from laminar to turbulent flow. This part compares the specific locations on the upper surface of the wing where the airflow transitions from laminar to turbulent. Normally, a rougher surface causes this transition point to move forward, because the airflow can no longer remain smooth once the surface becomes rough. In the transition gamma ray theta model, there is a range from 0 to 1, where 0 represents fully laminar flow and 1 represents fully turbulent flow. Here, I use the midpoint value 0.5 to indicate the transition location. It can be seen that for the same airfoil under the same speed and angle of attack, the transition point on the rough surface appears significantly earlier. So, is an earlier transition point a bad thing? At low angles of attack, such as during cruise, the laminar region becomes smaller while the turbulent region increases. This has only a slight effect on the pressure difference that generates lift, but it significantly increases skin friction drag. However, at medium to high angles of attack close to stall, a larger turbulent region can actually help. Because of its stronger surface attachment, it can delay flow separation and thus postpone the stall. So, how can we visualize the turbulent region and its intensity more clearly? Finally, I introduced TKE, turbulent kinetic energy, for a more intuitive evaluation. Turbulent kinetic energy represents the energy contained in turbulent motion, essentially describing the sum of velocity fluctuations averaged over time. It represents the local intensity of turbulence. On the rough surface, the turbulence intensity increases significantly, and the turbulent region appears earlier on the upper surface, which also confirms the earlier transition point. In addition, stronger turbulence can be observed near the trailing edge. Finally, we compare the performance results of each airfoil under smooth and rough surface conditions one by one. Here, the surface roughness is set to 0.0005 meters, which corresponds to a level between moderate and heavy roughness. First, taking GA30U314 as an example, we compare CD, CL, CL/CD, and CM. As expected, the CD is higher for the rough surface. Afterwards, I will make a comprehensive comparison of the results for all 4 airfoils. Under rough surface conditions, the CL decreases significantly with increasing angle of attack, and the maximum coefficient, CL max, occurs earlier and with a lower value. However, beyond the stall angle, the curve becomes more stable, which also confirms the previous observation that turbulence enhances the adhesion of the airflow to the wing surface. Due to the significant increase in CD, the efficiency ratio CL/CD on the rough surface decreases sharply. The reduction ratio will be compared afterwards. An interesting phenomenon can be observed in CM. The rough surface shows a steeper negative slope, indicating better longitudinal static stability. This can be explained by 2 reasons. 1. The rough surface delays the separation on the upper surface, causing the center of lift to shift rearward, which results in a more negative pitching moment. 2. The rough surface promotes an earlier transition of the boundary layer. The turbulent boundary layer, having stronger viscosity, delays the flow separation. Finally, all 4 airfoils are compared together. In terms of stall characteristics, the GA series shows smoother curves beyond the critical angle of attack, and both CL max and the corresponding angle of attack are the most favorable. In terms of aerodynamic efficiency, LS0413 performs best, although its advantage is not very significant. Compared with 314 performs slightly better due to its reduced thickness. Regarding longitudinal stability, NACA 23013.5 shows the greatest improvement, but the difference remains relatively small. Finally, I selected GA30U314 for the subsequent fluid structure interaction FSI simulations. Thank you for watching. If you have any suggestions or feedback, please feel free to leave me a comment. Thank you very much and see you in the next video.